Hello and welcome to NPTEL MOOC on electromagnetic waves in guided and wireless media. And in this module we study a very simplified element of many integrated optical circuits called a slab waveguide. We have already introduced the idea behind a waveguide in the previous module, where we imagined that we take a glass slab, okay, and then somehow couple light into this slab. We also saw how to couple light into that, and then if you think of this light propagating inside, light of course being an electromagnetic wave, if it is propagating inside this slab, provided that the slab refractive index, which we will take it to be N1, is actually greater than the refractive index outside, which we will take it as N2, which is less than N1, then these rays will undergo total internal reflection, and as they bounce back and forth between these walls, right, we see that effectively information or energy or the wave is actually propagating along the length of the slab. So, along the slab, which we will take that axis to be z axis. So, this wave would be propagating in this direction. However, we also saw that the ray picture that we have seen does not really tell us more information, especially no information is given or obtained in terms of what the electric field component would look like and what the magnetic field components or the magnetic field would look like corresponding to these rays, right. So, if you want to obtain this information, you need to use Maxwell's equations. Moreover, the geometric optics approach that we looked at in the previous module does not tell us even the existence of what is called as the evanescent wave, which we saw that will actually result when you go and approach this problem in the electromagnetic terms, right. That is to say, apply Maxwell's equations and you get a fuller picture than what is possible with the geometric optics. Sure, in some cases geometric optics approach, such as the one that we discussed, is actually quite simplified, and it is easy to use that picture to or qualitatively understand what is going on. But if you need quantitative answers, you have to like usually use electromagnetic equations, that is Maxwell's equations, and that is what we are going to do. Now, before we study the propagation in this slab waveguide, let me point out that this slab which we have taken is usually made out of, in the case of an integrated optical circuit, it is usually made out of substrates which are silica or other type of substrate. For example, it could be a lithium niobate, and you do not actually get only a slab, you get multi-layer structure, but propagation usually happens in only one layer. Okay, so, the other layers are for many different reasons, but propagation layer will actually happen in typically in one of the ones. I mean, you try to make light confined into one particular channel or one particular waveguide layer itself. Okay. So, I am simplifying the problem, I do not want to deal with many layers. Rather than that, we will simplify the problem to a single layer structure in which we have channel formed by a material whose refractive index is higher than the material refractive index outside. Now, in practice it is quite difficult to or it is not that difficult, but it is in practice you will not normally see such a symmetric slabs, especially in the integrated circuits, optical integrated circuits. What you actually see is another substrate or another material with a refractive index N3, which again is less than N1, but N3 can be greater than N2 or it can be less than N2. Okay. So, depending on this, the mode structures will vary slightly, but again this will introduce an additional layer of complication to our understanding of simple waveguides. So, I am going to give you only the principle behind the simplest of these waveguides called as the symmetric slab waveguides. Okay. So, in our module we will assume that outside medium is characterized by N2 itself. Okay. And you can think of a slab, okay, surrounded by these two by a medium, or this slab actually being carved out of in a medium whose refractive index is N2 and N2 is less than N1. Now, with Maxwell's equations we need to first determine what kind of coordinate systems are we going to deal with. So, we are going to use rectangular coordinate system, that seems very natural in this case. So, in that case we take this, anyway we have already taken this to be the z axis. What we will assume is that this axis over which these two the slab boundaries are defined are taken to be at x equal to plus a and at x equal to minus a. So, we center the coordinate system at this point. Clearly y will also be the coordinate, but that y will be coming out of this particular board. So, you have x, y and z as the coordinate system. Now, immediately we will have to deal with two things, right. It is clear that even if you go to the ray picture, it is clear that what we are dealing with is an obliquely incident wave, right. So, if we are dealing with obliquely incident, we have choices for transverse electric polarization or transverse magnetic polarization, meaning that light of course can be polarized in any way, but you can split that polarization into transverse electric and transverse magnetic, analyze them separately and then put the results back together. Okay. So, this polarization decoupling can be done because of the properties that any general polarized light can be split into two orthogonal polarizations of which TE and TM are, and then analyze them individually and then put the results back together. So, we are going to make a choice between TE or TM, and to keep the mathematics simple but still essential in showing you all the steps, I will assume that I am dealing with TE polarization. Okay. Note that at this point we have not said anything more about what would be the electric field and what would be the magnetic field for this polarized light and how would they behave in this region, the slab region or the region outside. And for later consistency with the fiber, we will call this region as core and we will call this as cladding. Okay. Although this is not really core and cladding in the fiber sense, but because our next model is going to deal with fiber propagation, that is propagation of light in fibers, we will keep the terms similar to that, and we call the dense refractive index region as core and the light refractive index region as the cladding which surrounds the core. Okay. So, accordingly the core width in our case is 2 times A, where A is the half core width. Okay. So, to summarize, we are going to deal with transverse electric polarized light. So far we have not said anything about the electric field and the magnetic field form or the solutions of the electric and magnetic fields in this scenario, and we have assumed a symmetric slab waveguide. Okay. Now, for transverse electric polarization, if you take this as the k vector that I have already drawn, then the magnetic field should be present, right. So, the magnetic field, if I take to be going along this particular direction, do not worry what the actual form of magnetic field is, we are going to derive this as the module progresses. However, for this case the electric field has to lie in, it is to come out of this page, right, it has to lie along y. So, electric field is polarized along y, and then the magnetic field will have two components, one is Hx and the other one is Hz. So, if you look at Hz component, that Hz component would go something like this, it would be along the z component, and then Hx component would be in this manner, right. Clearly onto this interface that we consider x equal to a and x equal to minus a, at these two boundaries Hz will be tangential to the boundary or tangential to the interface at x equal to a or x equal to minus a, whereas Hx will be the normal component. Okay. And electric field, because it is already in the y direction and y direction is parallel to this x equal to a plane or x equal to minus a plane, it is already tangential in this case. So, when you apply boundary conditions at the interface x equal to plus a and at x equal to minus a, you are going to apply boundary conditions on the tangential components, namely you are going to apply boundary conditions on Ey and Hz. Okay. So, we are going to see that one later on, but we will start with a simplest case. We will still assume uniform plane waves because, well, in this case we can still assume it to be uniform plane waves, or rather we will assume it to be plane waves. They are not really uniform in this coordinate system because there is a phase e power minus j k dot x which would be different, right. Anyway, so disregarding that short remark, let us write down what is the wave equation, and we already know the wave equation for plane waves, right, and that would be del square E plus k0 square n square E is equal to 0. Clearly I am dealing with only a single polarized case, that is E is basically Ey along the y direction, therefore I can drop this vector and then make this into a scalar equation. Okay. So, I am going to get a scalar equation with Ey. Of course, you will recognize this as Helmholtz equation, okay, which was actually possible, I mean for us it was possible to write this equation because we assumed waves to be plane wave kind of a thing, right. So, with the wave vector k given by k0 times n. N is of course refractive index. Now, here you have to think a little bit. Does this n refer to n1 or n2? In fact, you have to have two such equations, one for core and the other one for cladding. Okay. So, you will have another equation for the cladding. So, you will have k0 square n2 square Ey, okay, and this equation has to be solved separately, this equation has to be solved separately, and you meet both equations or match both equations at the boundary by applying appropriate boundary conditions. Okay. What would be the solution for the equation in N1, sorry, in the core region? Well, first look at del square. Del square in rectangular coordinate system is del square by del x square plus del square by del y square plus del square by del z square. Now, we are dealing with plane waves, we want the waves to propagate along z direction. So, I will assume that whether I am dealing with core or cladding, it does not matter, the electric and magnetic fields will always have an e to the power minus j beta z type of a propagation, right. So, we are we are propagating along the plus z direction, and we know this very well from our earlier discussion that a plane wave propagating along z will be described in this manner, e power minus j beta z type of a solution. What it means is that this del square by del z square can be replaced by minus beta square. Okay. Because our structure actually is taken to be kind of infinite in the x and y plane, and none of the components are actually dependent on y, we can make this del square by del y square term go to 0. Okay. So, I am going to make this del square by del y square term go to 0, and what I am now left with this del square operator is del square by del x square minus beta square. Okay. I can put this operator onto Ey. So, what do I get? And because now Ey is going to be function only of x, okay. Of course, it will also be function of z, but that z function is already taken to be in the form of e power minus j beta z. Okay. So, I can replace all these partial derivatives with the knowledge that along z is this behavior, however, along x we still do not know what is the behavior. So, we are going to find that out, right. So, I can write down the equation which says d square Ey by dx square plus k0 square. For the moment I am going to consider the solutions in core region. So, I can write this as k0 square n1 square minus beta square Ey equals 0. Okay. This is your ordinary second order differential equation, nothing fancy about this. The solutions of course can be in the form of an exponential signals, right, or exponential functions. So, if you go back to your high school or rather your differential equations course, you will see that you can write this as minus s square Ey, okay, or you can you can write this as minus s square Ey, where s square is equal to k0 square n1 square minus beta square. Okay. And the solutions for this one will be e to the power plus or minus jsx, right, or you have a solutions in the form of cos sx or sin sx, right. If s square were to be negative, that is when beta square is actually greater than k0 square n1 square, then this would be a positive quantity which we will call as some gamma square, okay, and the solutions would have been e to the power plus or minus gamma x. Okay. The nature of these two solutions are very clear. One of them is an oscillatory solution. So, a cosine x would go in this manner, a sin x would go in this manner, a sin sx, whereas e power plus or minus gamma x, one would be decaying, the other one would be increasing, right. Of course, we do not have any gain. So, normally we can rule this out in our solution set, but these three seem to be the solutions that we are looking for, but exactly which solution needs to be used depends on the sign of this term s. Okay. In the core region, we do not want any decay along x, meaning that we want in the core a solution to be in the form of cosine or a sine wave. That actually means that k0 square n1 square must be greater than beta square, and instead of calling this s square as k0 square n1 square minus beta square, we will go with the more conventional notation that is used in optics. We will call this as kappa f square, okay, or we will call this simply as kappa square. Okay. So, we will call this as kappa square, and we demand that this kappa square be actually a positive quantity, okay, which means that the solutions for Ey in the core will be of the form A cosine kappa x plus B sin kappa x. We do not know what the A and B constants are, we can find this out, or we are going to make one more simplification. We will assume arbitrarily that B is equal to 0. I am ruling out this solution because only A cos kappa x is also a solution of this equation, okay, with an unknown value of A. And if we retain only the cosine type of solutions with respect to Ey as a function of x, these are called as even mode solutions, obviously because cosine is an even function, and because I have ruled out this sine function, they are called as odd mode solutions. Okay. However, I can obtain odd mode solutions by ruling out the even mode solution arbitrarily. Okay. In practice, you can have both modes and the overall structure can be of a combination of these two, but we will soon see that these two modes do not exactly propagate at the same propagation constant, and therefore they can be discriminated against. Okay. I am taking the even mode only for simplicity, and I will leave this as an exercise for you to repeat the entire calculation, assuming that we are dealing with a odd mode functions or an odd function. Okay. So, yes, we have now shown that the solution in the core would be of this form. What would be the solution for cladding? What would be the solution that you would expect for cladding? Well, I know that if at all this is in the form of a sinusoidal function or a cosine function, right, then outside we must have an evanescent wave which of course decays as you move away from the interface, right. So, that is what we have already seen, and the same behavior should be expected even in the down, in this side of the cladding as well. So, what we hope for the solutions in the cladding would be of the form C e power minus gamma x minus a. I will tell you what gamma is in a minute, and then you have d e power minus gamma e power gamma plus x plus a. The reason why we have taken x minus a is just to simplify the exponential function, cos at x equal to a this will be just c, and at x equal to minus a this will be equal to d. Of course, from symmetry conditions you would expect c to be equal to d, and that is actually true. Okay. So, the solution will decay exponentially on both sides with the same decay coefficient and with the same starting point at the boundary. Okay. Now, what is gamma? Remember, these solutions in the cladding are actually the solutions of Helmholtz equation d square Ey by dx square plus k0 square n2 square minus beta square. Okay. If you ask or if you demand that beta is greater than k0 square n2 square, okay, then you see that beta is greater than k0 n2, not n2 square. When beta is greater than k0 n2, clearly that you are going to, it is clear that you are going to get a decaying solutions for Ey, which is what you have actually gotten here. Okay. I have shifted the coordinate system on the exponential by making instead of e power minus gamma x, I have made it into e power minus gamma x minus a. If I do not shift the solution, then that extra term will also be present in the solution, but that would be a constant. Okay. So, it does not matter if you just take e power minus gamma x, but to simplify the boundary conditions I have just moved the coordinate system for the exponential to be along or to be starting at x equal to plus a or at minus a. Okay. Now, we have the full set of solution, we can now go to the next step. What is my next step? Next step graphically I have already shown. Basically, what you are trying to do is to find out what would be the values of a and c for a given kappa and gamma, or you are even adjusting kappa and gamma in such a way that the solution smoothly changes over from this cosine wave in the core onto an exponentially decaying wave in the cladding. Okay. So, that is what graphically we are doing, but mathematically what that would mean is at x equal to a boundary you have a cos kappa a, which would be equal to c, which is obtained by making x equal to taking x equal to a in this equations. So, what you have is a cos kappa a equal to c. At this point I do not know what a and c are, but that is fine, we will leave this expression here. Now, I will not get much by applying the boundary condition at x equal to minus a. Instead, what I want is a boundary condition on hz, right, or I need a form for hz. But how do I find hz? Well, I know Maxwell's equation, it tells me that del cross E is equal to minus j omega mu naught times h, correct, and I know E is along Ey, expand in this del cross E and equating the terms on the left hand and the right hand side, which again I will leave as an exercise because we do not have much of a time. You can show that Hz will be equal to minus 1 by j omega mu naught dEy by dx. Okay. So, you can show that this is what you are going to get, and once you know what is, once you know the expression for Hz and you know the expression for Ey in the core and cladding separately, so you can differentiate it. So, for the magnetic field component Hz, you will get a solution which would be kappa by j omega mu naught A sin kappa x, and on the cladding side you get gamma c by j omega mu naught times e to the power minus gamma x minus a. Okay. So, these are the solutions. Here I will leave it as an exercise for you to show that the solution will be minus gamma c by j omega mu naught e to the power gamma x plus a. Please note that this region is basically x greater than minus a, okay, and this region is basically x greater than a, and of course this region is where minus a is less than x less than a. Now, you can apply boundary condition at x equal to a for the tangential magnetic field, that is Hz component, and once you apply the boundary condition for Hz component, what you get is kappa a sin kappa a from this expression should be equal to gamma times c, okay, because at x equal to a this exponential will be 1 and j omega mu naught on both sides will actually cancel off. So, you get this kappa a sin kappa a is equal to gamma c. We already know that c is given by a cos kappa a. So, I can replace in this expression c by a. So, I have gamma a cos kappa a. Indeed, arranging the terms you get tan kappa a to be equal to, so a will cancel on both sides, sin by cosine is tan kappa a, you get gamma by kappa. Okay. So, this is an interesting expression. Unfortunately, it does not have straightforward solutions. The solutions that you are going to get are all what is called as numerical solutions, because you have a function of the form tan x equals x, and this solution is rather easily found using graphical methods or numerical methods. Graphically, what this is telling you is that you have x in this manner and then you have say tan kappa x. So, you have this expression and then again this one, these are the solution that you are going to get for tan, right. So, if you plot this as a function of x, these are the solutions, and all the intersections that you are going to get will be the solutions. Okay. And of course, what you have observed is that there are multiple solutions for this tan x equal to x kind of a solution, right. In our case, what we have is tan kappa a is equal to gamma by kappa. Okay. If I multiply on both sides by a and then define kappa a as equal to u and gamma a as w, okay, then I can even rewrite this equation as tan u is equal to w by u. Okay. And what is u? U is basically kappa times a, and what is kappa? Kappa is square root of k0 square n1 square minus beta square, okay, times a. Now, w of course is given by square root of beta square minus k0 square n2 square times a, and what you observe here is that this equation that we have written tan u equals w by u implicitly contains beta. So, the solution method that we normally adopt is to express this w in terms of u, and you can actually do that by writing u square plus w square as what is called as v square. What is this u square plus w square? That is basically k0 square n1 square minus n2 square times a square, which we will define as parameter v, and v is an important parameter that is determined only by the waveguide, geometry and materials. In this case, it is only determined by the waveguide, material property and the operation wavelength lambda, right. Waveguide has a radius a which is known, lambda is the operating wavelength which is also known, n1 and n2 of the waveguide are also known or usually can be designed knowing certain other properties of this v. But the important point is that the solution that you obtain will be of two steps. Okay. After you express w as v square minus u square under root, so on the left hand side you have a function of u, right hand side also you have a function only of u, and you can plot the solution as a function of u, or rather plot the left hand side and the right hand side as a function of u. Okay. So, on the left hand side it is just a tan function, it will have different values in this manner. So, this will be 0, this will be say, so this is at pi by 2, this is at pi and so on, it is a periodic solution, right. And on the left hand side what will happen at when u is very small, when u goes to 0, this numerator is finite, denominator is infinite. So, you will start somewhere of the infinity value, and as u starts to increase it will go to 0 at u is equal to v. So, if you know what is the value of v as determined by, let us say, your properties of the material or properties of the waveguide, you would actually get a value of v here, which is determined only by the waveguide. And now your solution has to be until this point, right. So, you start off with infinity and then you go to the solution until at this point where it kind of decays off. How many intersections do you see? You see 2 intersections. One intersection here that corresponds to the fundamental mode that would be propagating, and this next one is called as the higher order mode that would be propagating. So, in fact, you get multiple modes which are propagating. The first intersection of this one will be denoted as TE1 mode, the next one will be denoted as TE2 mode and so on, and these are all the even modes that we have considered. Okay. In the odd mode scenario things are slightly different, there the relation on the right hand side or the left hand side actually changes slightly, and without going too much into details you can plot the odd mode cases, and what you observe is an intersection which would be present in this manner as well until this value of v here, and what you notice is that you will first get an even mode, then you will get an odd mode, then you will get an even mode. Odd modes are basically sine functions, okay, and the higher order modes, the cosine functions are the even order functions. So, if you were to look at the fundamental mode, assuming that this is your boundary for the core and cladding, the odd mode would look, sorry, even mode would look something like this. This is the cosine wave and then it is exponentially decaying everywhere, and the even mode would look something like this. Okay. So, these are the even, I am not drawn the pictures nicely, but this is how the even and odd modes would look like, and these are the fundamental modes. The higher order modes will be will have more maxima in between. So, this completes our basic understanding of waveguide modes. So, the takeaway message from this module is that mode is essentially solution of wave equation or equivalently Maxwell's equation, meaning solution meaning the E and H patterns that I am actually interested in, or the E and H solutions that I am interested in, and this should not only be the solution of Maxwell's equations, but they should also satisfy boundary conditions. Okay. In the free space case, these modes were essentially plane waves. They were actually in the form of e power minus j beta z for a z propagating wave, or e power plus j beta z for a minus z propagating waves. Okay. There were no boundaries. However, the modes you can think of, the free space modes, were the plane waves. However, the mode structure in the case of a guided thing is actually very different. So, in the guided media, the mode structure depends on the geometry. For the case of a planar waveguide that we have considered, or what is called as a slab waveguide, the mode structure is either cosine or sine with many periods within the core and decaying exponentially in the cladding, of course propagating along the waveguide itself, right. So, what you have to understand is that this waveguide mode or mode in general is a property of the geometry. When there is no geometry, when there is no constraint, you get a plane wave, but when you start putting constraint, the solution changes over, and depending on the type of the constraint that you put in, that is if you send in parallel plates, the solutions inside will be given by sinusoidal functions, it will be cosine or sinusoidal. However, if you, instead of shrinking this, putting this one in this manner, if you make cylinders, the functions will still look like sine and cosine, but they will be mathematically actually Bessel functions. Okay. So, the type of geometry determines the form of the function or form of the electric and magnetic fields that can propagate within the given waveguide, and the solution of Maxwell's equation, which also satisfies boundary conditions, is called as a mode, and we have just successfully solved for modes of a symmetric slab waveguide. Thank you very much.